Usually when you look at a computer screen, yeah, well, you don't really think about the hardware.
Right, you don't. It's just not what you're focused on.
Exactly. You see the folders, the mouse pointer, the web browser. It's a user interface built to make sense to your human brain. You drag a file to the trash can, and it just disappears.
Yeah, but underneath that, I mean, there's no actual folder. There's no physical trash can sitting inside your laptop.
Right. It's just billions of microscopic transistors flipping zeros and ones. The interface is just a rendering, like a translation of the hardware, so that you can actually interact with it.
Exactly. It's an illusion of convenience. We interact with the translation, not the native reality itself.
Right. But what if, and stick with me here because this is wild, what if the entire universe is exactly like that?
Like a user interface.
Yes. What if the physics we think we understand, everything from, the massive proton to the expansion of the cosmos, is just a translated user interface running on an entirely different set of foundational hardware?
It's a pretty massive idea.
It is. Today, we're taking a deep dive into a completely mind-bending physics paper titled Tetrahedron Particle Derivations and Lattice Native Closure. Our mission is to decode this thing.
Which is no small feat, honestly.
Definitely not. But we are ditching the dense physics jargon to translate a radically new understanding of how reality source code actually works.
And we should note right up front, this paper isn't just a philosophical thought experiment. It is a highly structured, mathematically rigorous framework.
Right, with actual proofs and lemmas.
Yes. It is attempting to prove that our standard model of physics is fundamentally a mistranslation of a much simpler underlying geometric reality.
Okay, let's unpack this. Because to understand this mistranslation, we really have to start with the geometry of space itself.
Right, the background grid.
Yeah. The interface we've been using, which the paper argues is essentially a cubic shell.
That's right. So if you imagine a primitive, microscopic point in space as a cube, it has 26 neighboring directions you could theoretically move in.
Wait, 26. Let me visualize that. How do we get 26?
Well, think of a Rubik's Cube. You have the center cube, which is you. How many cubes surround you?
Oh, okay, so I have 6 faces up, down, left, right, forward, back.
Exactly. Then you have 12 edges where those faces meet. And finally, you have the 8 corners. 6 plus 12 plus 8.
Ah, okay. I see it now. 26 directions.
Right. So standard physics builds its equations, assuming a particle can move or interact in any of those 26 directions.
Got it. So that 26 direction grid is essentially the operating system of the standard model.
Exactly. But the paper asserts that this cubic grid is an illusion. At the absolute lowest, most fundamental hardware level, space isn't a cube, it's tetrahedron.
Meaning a tetrahedron,
Yeah.
like a pyramid with a triangular base.
Precisely.
Yeah.
And a tetrahedron only has 4 faces, which means each primitive site in the universe's hardware only has exactly 4 interaction ports.
Not 26, just 4.
Just 4.
It's like trying to play a deeply complex, modern PC game that requires a massive keyboard, but you are forcing the game to run on a retro 4-button controller. Up, down, left, right.
That is a very apt way to look at it, and this geometric conflict is the literal root of the mistranslation.
Because of those extra directions.
Yes. If our native hardware only has 4 ports, but all of our traditional physics equations are desperately trying to describe a 26-port space, the math literally leaves us with 22 ghost directions.
Because 26 minus 4 is 22. So standard physics is calculating for 22 channels of information that just don't physically exist in the hardware.
Right, and the paper calls this the near-miss principle.
Near miss.
Yeah, because we have been mathematically distributing physical properties, forces, energy, momentum, across 22 non-existent channels.
So all of our standard physics calculations are fundamentally near misses.
Exactly. They require constant, arbitrary fitted corrections just to make the equations work. We have been dragging around massive amounts of translation overhead simply because we are calculating for ghosts.
But hold on. If space itself is just this massive microscopic network of 4 port nodes handing off information,
Right.
what the heck is a particle? Because usually we are taught to think of particles like electrons or quarks as tiny, solid billiard balls.
Yeah.
Physical stuff.
Well, I mean, that's the cubic interface talking.
Yeah.
In this tetrahedron framework, particles are not physical stuff at all. They are defined as closures.
Closures, like a loop.
Yes, think of them as stable, not like transport patterns winding through that four-port lattice. They aren't solid objects sitting passively in the grid.
Okay, so what are they doing?
They are self-sustaining loops of traffic. The information routes through the four ports in such a perfect sequence that it ties a knot in the network, endlessly handing off its data in a closed loop.
So a particle is literally just a stable traffic pattern that refuses to untie itself.
Pretty much, yeah.
But how does a traffic pattern exert a physical force? For instance, the strong nuclear force. That's the incredibly powerful glue that holds the nucleus of an atom together.
Right.
If there's no stuff, where does that force actually come from?
What's fascinating here is how the paper solves the mystery of that exact force using pure geometry.
Pure geometry.
Yeah. In traditional physics, the strength of the strong nuclear force relies on a seemingly arbitrary constant. It's just an empirical number physicists observed, measured, and plugged into their equations to make the math balance out.
Right. They don't know why it's that specific number. It's just treated as a given rule of the universe.
Exactly. But in this four-port framework, it's not a magical force constant, it's just a handoff cadence.
A handoff cadence. Okay, explain that.
Let's look at a baryon like a proton, which is held together by the strong force. A proton is made of three constituents, which we call quarks.
Okay, three constituents. Got it.
If each of those three constituents operates on a native four-port node, they combine to make a 12-port structure.
Right, 3 times 4.
The strong force is simply the native frequency at which this specific 12-port closure updates itself on the network.
Oh, wow.
Yeah. If you calculate that on the native hardware, the cadence is the square root of 2 divided by 12. That comes out to roughly 0.11785.
And what does our traditional cubic physics say the number is?
Our cubic physics takes those same three constituents, but falsely projects them across the 26-direction grid. 3 divided by 26 gives you about 0.11538.
Which is incredibly close.
But a near miss.
Right. So our standard measurement of the strong force is really just a shadow of the real mathematical frequency.
Exactly. Confinement, that glue holding the atom together, isn't an invisible mystical energy field. It's just the physical maintenance cycle of a 12-port loop updating itself on the network.
Here's where it gets really interesting, though. If a particle is just a closed traffic loop, and fundamental forces are just the update frequencies of those loops.
Yeah.
What is mass? Because if I pick up a bowling ball, it's heavy. If there's no solid stuff, why do things have actual physical weight?
Well, the paper redefines mass entirely. Mass is not weight. Mass is not stuffness. Mass is a persistence burden.
A persistence burden. What does that mean?
Think about it from the network's perspective. It requires computational effort, a node agreement cost, to stop this knot of traffic from unraveling back into empty space.
Oh, I see.
The network has to constantly work to maintain this specific, complex traffic pattern against the chaotic background of the universe.
It's exactly like server maintenance costs.
Yes, that's actually a perfect way to look at it.
Like if I code a super simple, bare-bones, one-page website, it costs me almost nothing to keep it online. The server barely has to think about it.
Right.
But if I build a massive, complex, real-time global database with millions of users, the server load is huge. The persistence burden is massive.
That is a brilliant way to frame it. And the paper actually runs the exact mathematical server costs for different particles.
Wait, they calculated the server load of a particle.
They did. Let's look at an electron. It is a fundamental, minimal, stable loop. It operates across the 4 native ports in a straightforward 4-step cycle.
Okay.
4 ports to the power of 4 steps. That gives us a configuration regime of 256.
Okay, so the server load to keep an electron existing is 256.
Right. Now let's look at the proton we mentioned earlier. It isn't a simple loop. It has 3 subcomponents.
Right, the quarks.
And to keep those 3 components bound together as a single proton, the network has to route them through a vastly more complex 9-step internal sequence.
So 3 components to the power of a 9-step routing sequence. 3 to the power of 9, that's 19,683.
Exactly. A proton isn't heavier because it's filled with a denser physical material.
It's heavier simply because it's not is vastly more mathematically expensive to maintain.
Yes. The mass hierarchy of the entire particle spectrum, why some particles are light and others are incredibly heavy, is literally just a hierarchy of how much processing power these different geometric knots require to stay tied.
Okay, that is incredibly elegant. It takes something we experience as a raw physical reality, weight, and grounds it in pure computational logic.
It really cleans up the foundational concepts.
But I have to play devil's advocate here. I can accept the server analogy, But if our entire physics model is a mistranslation like a 26-key keyboard trying to play a 4-button game, shouldn't we see proof of that translation error?
What kind of proof?
Well, if we're forcing 4 ports into 26, the math shouldn't divide perfectly. There should be mathematical scraps left over. Where is the evidence of this mismatch?
You've just hit on one of the most compelling arguments in the entire framework, the fine structure constant.
Oh, the famous number 137.
Yes. In standard physics, the inverse fine structure constant governs the strength of electromagnetic interactions, basically how light interacts with matter, and the number is roughly 137.036.
And just like the strong force, traditional physics has no idea why it's exactly 137.036.
None at all. It's arguably the most famous unexplained empirical input in physics, but this paper's framework breaks that number down.
How so?
It completely separates the clean integer 137, which it defines as the discrete handoff threshold of the network, from that tiny fractional remainder, the 0.036.
Wait, is that 0.036? Is that the translation scrap?
The paper explicitly defines that 0.036 as the orphan residue. It is the literal quantitative signature of forcing 4-port geometry into 26-port math.
It's the cutting room floor. It's like when you exchange currency at a bank or use a complex algorithm to convert dollars to euros.
Exactly. You always lose a tiny fraction.
Right. There's always that tiny piece of a cent left over because the algorithmic exchange rate doesn't divide perfectly into whole numbers.
And you can't just hand someone 0.036 of a penny.
Exactly.
Yeah.
But over billions of transactions, those fractional pennies pile up. So what this paper is saying is that this tiny fraction, this 0.036, isn't random experimental noise.
No, not at all.
It is the mathematical fingerprint proving that an exchange, a translation between 4 ports in 26 directions actually occurred.
Precisely. Those scraps aren't an embarrassment to the equations. They are the absolute proof of the underlying geometry.
That is wild.
And this geometric mismatch explains another massive, long-standing mystery in physics: weak chirality, or what physicists generally call handedness.
Okay, slow down, because parity violation and handedness have always confused me.
It confuses a lot of people.
As I understand it, the universe has this weird, inherent preference for left-handedness in certain particle interactions, specifically with the weak nuclear force. Like, particles spinning one way decay perfectly, but if you perfectly mirror them to spin the other way, the universe just kind of rejects it.
Right, that's the standard view.
It's always felt like an arbitrary, asymmetrical rule tacked onto the universe.
Well, it does feel arbitrary in a cubic space, because a cube is perfectly symmetrical.
Right.
But if we connect this to the bigger picture, the native hardware is a tetrahedron, a pyramid. And unlike a perfect cube, a pyramid lacks perfect inversion symmetry.
What does that mean in terms of the traffic we were talking about earlier?
Let's use a real-world driving analogy. Imagine you are driving through a complex 3D cloverleaf highway intersection. The physical roads, the banks, the ramps are all engineered so that if you take an ordered sequence of left turns, your car glides through smoothly.
Okay, so that's a left admissible closure. The traffic flows perfectly.
Now, what happens if you mathematically mirror your route and try to take all right turns on that exact same physical highway architecture?
Well, the ramps aren't banked for that. You'd be driving against the flow of traffic, hitting physical barriers, having to stop and reverse. I mean, it would be a complete traffic jam.
Exactly. On a 4-port tetrahedral node, an ordered sequence of paths moving through those ports is not equivalent to its exact mirror reversal.
Because the geometry isn't a cube.
Right. The leftward path slides through the node below the energetic cost threshold, but its exact mirror image incurs what the paper calls inversion debt.
Inversion debt?
Yeah, the energy cost to process that mirrored right-turning traffic pattern is simply too high for the network to easily accept.
So handedness isn't a magical law of physics. It's just the physical reality. That on a pyramid-shaped grid, some knots tie easily, and their mirror images literally jam the system.
Exactly. The universe isn't biased against right-handed particles. It just can't afford the inversion debt to route them through a tetrahedral port.
So what does this all mean for how things actually move? Because if a particle is just a traffic pattern, localized knot in the network, how does it get from point A to point B?
This is where we hit what the paper calls the no-elevator theorem.
The no-elevator theorem.
Yeah. In our cubic user interface reality, we think of motion as just sliding a solid object from one spatial coordinate to another, like putting a box in an elevator and just smoothly sliding it up to the next floor.
Right. The box itself doesn't change. only its location changes.
But on this tetranative substrate, you cannot simply translate across the network without rotating. You cannot slide. You must wind through the ports.
Wait, so I can't just pick up the knot and move it?
No. To move, the knot has to sequentially untie itself from one node and precisely retie itself on the next adjacent node.
Oh, wow.
Every single step of motion physically updates the internal winding state of the particle.
So a particle's motion and its core identity are completely inseparable.
Exactly.
It isn't a static object that later decides to take a trip. Moving is the act of recomputing its own existence, one node at a time.
It is by definition a stable transport grammar.
I am tracking with this, but it brings up one final ultimate scale question.
Okay, what's that?
We've been talking entirely about internal systems nodes handing off update tokens to adjacent nodes. But what happens when the substrate runs out of room?
Ah, the boundary.
Yeah. What happens if an update token moving through this grid reaches the literal outer edge of the universe, and there is no next node to hand the token to?
That brings us to the native growth law of the substrate, which the paper calls boundary reconciliation.
Boundary reconciliation. What exactly does it reconcile?
Well, when an update token hits an exposed boundary port like the absolute edge of reality and fails to hand off its information because there's nothing there, that unspent token doesn't just disappear.
Right, conservation of energy. The energy has to go somewhere.
Exactly. So the network converts that failed handoff into a new spatial unit. It mints a new node. It becomes delta S.
Wait, it literally creates new space.
Yes. And here is where the framework offers its most profound, poetic realization. It reveals that heat and cosmic expansion are actually the exact same mechanical rule.
Heat and cosmic expansion.
Yeah, they're just scale separated.
Wait, slow down. Heat, like the heat inside my oven.
Yeah, think about a closed box. An internal system where there are no exposed boundary ports.
Okay.
If a handoff fails inside that closed network, maybe two traffic patterns collide and the network can't process the debt, that unresolved Braden remains trapped internally.
Right, it can't just mint a new node inside a closed box.
Exactly. It becomes kinetic disorder. We experience that internal failed handoff as heat.
Okay, so a failed handoff inside the system is thermal energy.
But now zoom all the way out to the open boundary of the universe. The absolute edge.
Where there is an exposed edge.
Right. When that exact same failed handoff rule applies at the boundary, it doesn't bounce back as heat. The failed handoff converts into a new native node.
Oh my God.
Cosmic expansion isn't the universe magically stretching like a balloon.
It's a literally boundary minting.
Exactly. The network is endlessly laying down more floorboards at the very edge of the universe every single time an internal token hits the wall and fails to pass.
That is.
Yeah.
Wow. So the heat in my coffee cup and the accelerated expansion of the cosmos are the exact same algorithmic bug in the code, just happening in different locations.
Yes. Internal friction creates heat. External friction creates space.
That is simply unbelievable.
And it all wraps up nicely into one final cohesive thought from the paper, the compression theorem.
Okay, summarizing it all.
Think about what we just did. We took the most complex mysteries of standard physics, the strength of forces, the mass of particles, chiral asymmetry, and cosmic expansion.
And we compressed them all down to substrate native geometry.
Exactly. Handoffs, persistence burdens, and boundary errors. It proves that the standard model of physics is exactly what we said at the start. It's just the rendered user interface.
Thank you for going on this intense mental journey with us today. This paper challenges literally everything we are taught about reality, but I really hope that after today, you look at the physical world differently.
It's a lot to process, for sure.
It really is. From the weight of a stone in your hand to the sheer expanse of the night sky, it's all just a symphony of four-port geometry, endlessly trying to balance its books.
This raises an important question, though, a final thought to leave you with.
Let's hear it.
If the physics we experience, daily gravity, mass, light, is just a user interface translating a deeper four-port hardware grammar, does that mean that one day, if we learn to speak the native language perfectly, we could bypass the interface entirely? Could we eventually reprogram the hardware of reality itself?
Man. I guess the next time you find yourself stuck fighting against the limitations of reality, maybe you don't need a bigger, better 26-key keyboard. Maybe you just need to find the native 4-button controller. Until next time, keep diving deep.